Okay, so part two of Newton's law of restitution. We're going to do a few more problems on this topic. Just before we start, question for you. If I have two balls of different sizes and they're traveling towards each other, let's say they're the sizes roughly shown in the picture, and they both have a horizontal speed of 1 meter per second. Note that that's speed, obviously they're heading towards each other. So they collide. And let's say the collision is perfectly elastic. So this pair of objects, they have an E equal to 1. What can you conclude about their subsequent horizontal velocity? So any thoughts on what I might be trying to get at here? It's not going to be necessarily the simple answer. So what do you think the answer might be on what's going to happen? You can pause and have a think. So in this case, what we can conclude about the horizontal velocity is that their horizontal velocities are not going to be having a total which is the same as their original horizontal velocities, even though the E is 1. And the reason for this is because of the fact that they're different sizes. So later on in the chapter, we will start to talk about these kinds of situations, I think. But for the time being, we need to assume that when objects collide, not only is the E equal to 1, but their point of contact is also horizontal. So the problem with them being a different size is that, well, putting it to an extreme, right? Imagine if you had a very tiny object and a very big object like this, right? If they're on a surface like that, when they hit, it's not going to be a neat collision. What effectively ends up happening is one of them ends up being knocked upwards a little bit, and one of them ends up being knocked downwards into the ground a little bit, and presumably bouncing off the ground. The E can still be 1. All that means is that the velocities end up being have a total which is the same as the original total. But because I specified horizontal velocity, the horizontal component is actually not going to add up to what it was originally. So that's the point I'm trying to make here. When two objects collide, if they're the same size, that's good. If they're different sizes, then we're not going to have a nice, neat horizontal collision. And part of that is because the point of contact, in this case, the point of contact is almost going to be a vertical tangent, whereas these two objects here, they're almost going to have a slanted tangent along their points of contact, which means that not all of the original velocity ends up in the final velocity going horizontal. Okay, so that's it. That's the point I wanted to make there. Hopefully there's a bit of intuition to it, but we'll learn more about the mathematics at a later date. So we're now going to look at a few problems where we have to make more use of inequalities to solve the problems. So before we do that, I just want to make a point on a few things I'm calling hidden inequalities. And that is information that you already may know mathematically about a scenario, which you may take for granted. So the first of these is quite a basic one. It's you know for a fact that E is always less than or equal to 1 and it's always greater than or equal to 0. So if you're ever given a scenario involving multiple velocities and you're asked to show some sort of relationship between them, you already have a relationship for free. You know that this is always true. So it's not really hidden, but it may not be stated explicitly in a question, but you are allowed to assume it because it is of course true. E is always between 0 and 1. Another one, fairly obvious. We know masses are always greater than or equal to 0. Let's, in fact, get rid of the edge case. Masses are always greater than 0. Another hidden equality you can always assume. And the other one is a bit more subtle. and that is as follows. If an object has velocity u, and changes direction, I guess what I'm trying to say is, if you're told that an object changes direction, what that's effectively giving you in mathematical terms is, we have no idea what the magnitude of the velocity is, but we know that the sign changed. So if you had an object and you said its u was greater than 0 and it changes direction, then that means its v is definitely less than 0. Correspondingly, if you were originally told it was, say, going to the left, taking right as positive, then u is less than 0, and if it changes direction, you now know v is greater than 0. And in addition to that, if you're told it doesn't change direction, then of course you're going to keep the inequalities the same. So if you ever get any wording in a question which says, you know, the object changed direction or it didn't change direction, this is how you need to set it up in terms of inequalities. State the final velocity as either being greater than or less than 0 accordingly. Okay, cool. So with that said, let's take a look at an example. So things getting a little bit more algebraic here, a lot more unknowns. We've got two objects, their masses are 3m and 4m, moving in opposite directions but towards each other. I'm going to call P is 1 and Q is 2. Immediately before they collide, P has speed 3u. So I'm going to take u as being a vector and take right as positive 3u, and Q has speed 2u. So expressing that as a vector, I'm actually going to write this as minus 2u, where u is then a constant, is a scalar. So let me just note that down so we don't forget. Okay, u is a scalar, and 3u is the vector which corresponds to P's initial velocity, and minus 2u is the vector which corresponds to Q's initial velocity. The coefficient of restitution is E, but it doesn't tell us what it is. By modelling the balls as smooth spheres and the floor as a smooth horizontal plane, it's assumed they're the same size as well. Show that the speed of Q after the collision is this. Okay, so let's do a bit of algebra. Let's start with restitution. In terms of their final speeds, we need to give a name to those. Let's also just note that then, that this is initial, this is final, and let's just say it's v1 and v2 vectors. We don't know what their directions are. Okay, now we can do the restitution. E is equal to v2 minus v1 all over u1 is 3 minus 2u. So that gives us v2 minus v1 all over 5u. Okay. And then conservation of momentum tells us that 3m times 3u plus, well, let's already put the minus there, minus 4m lots of 2u. So I just took that minus from minus 2u and put it here. That's equal to 3m v1 plus 4m v2. So that gives us 9mu minus 8mu, it's actually just mu, isn't it, equals this. Notice that the m conveniently cancels. So we have u equals 3v1 plus 4v2. Okay, I'm going to make some space and just rewrite the key results here for a moment. And for the E, we've got E equals this thing. So let's multiply both sides by 5u and just get this. Looks a bit simpler. And then we'll make some space. So we've got a relationship between v1, v2, and u and e. And what are we being asked to find? Just a reminder, the speed of q. So the speed of q, that's our 2 object. We want v2 here. So what is v2? v2 is equal to v1 plus 5 eu. And v1 is equal to, using this one, v1 is equal to u minus 4v2 all over 3. Therefore v2 is equal to u minus 4v2 all over 3, let's not do too much at once, plus 5 EU, which is 15 EU over 3. That's then equal to, oh no, I've confused myself a bit there, sorry, substituted the wrong thing. V2 is equal to, must be a faster way to do this. Okay, I'm sure one of you has spotted it. I'm actually just going to multiply that second equation by 3. I think that makes things a bit easier. So that second equation is 3v2 minus 3v1 equals 15 EU. So now that 3v1 and that minus 3v1 are going to cancel out nicely. We'll add both sides together. So we get, left to right and right to left. So we'll end up with 7v2 equals, so that's that plus that is 7v2. And this plus this, yeah, this is going to work much better, is 15 EU plus u. We get v2 equals a seventh of u times 15e plus 1, yes, which is what we wanted. Okay, so that's part A done. Hopefully you spotted also with the simultaneous equations. That was an easier way to do that. Cool. All right, let's look at part B. Given that the direction of motion of P is unchanged, find the range of possible values of E. Okay. So, this is the one where it's a bit tricky if you don't know how to write this mathematically, right? So remember what I said about these hidden inequalities. The direction of motion of P is unchanged is a statement about the final velocity of P, which is our number 1 object. It's a statement about V1. It's saying, well, in the first instance, this object P on the left, it was moving to the right. It had a positive velocity, so U1 was positive. If the motion is unchanged, the direction of it is unchanged, then V2 is still greater than V1 is still greater than or equal to 0, right? Or is greater than 0. So this part here is saying V1 is greater than 0. Find the range of possible values of V. Now, annoyingly, we've just found V2 here. So what we could have done, if it was talking about Q, is say that's greater than 0 and then find an inequality. However, it's V1. So what we need to do, so this is the logical sequence of steps, is we identify it's an inequality in V1. Now we need to find V1 in terms of E and little u, in the same way we just did for V2. So let's do that. In fact, we can probably make use of, we've got a lot of equations going on. Let's use that one and this one to get an expression for V1. So V1, using the first orange box, is equal to V2 minus 5 EU. And then using the second orange box, we substitute in V2, so we get this. And we should be able to combine all that. So if I change that 5 to a 35, so that is now over 7, we end up, I'll write it over here, V1 is equal to a 7th U of 15E plus 1 minus 35E. And then 15E minus 35E is minus 20E. So let's just write that in directly. Yeah, and that's correct. So V1 is this, and we've been told V1 is greater than 0. Okay, so again, let's clear some space. This question has quite a lot of parts to it. V1 is greater than 0. So therefore, we're just going to set that whole expression greater than 0 and then rearrange to eventually find the possible values of E. So if a 7th U, 1 minus 20E is greater than 0, that's the same as saying U times 1 minus 20E is greater than 0. Okay, so I've already got rid of the 7th. We don't need it. Now we've got to be careful. What do we know about U? Well, by definition, we said 3U is the vector going right, so therefore U is a positive number. Because U is positive, I can divide both sides by U. 0 divided by U is 0, and we just have this. If it was negative, then I'd have to flip the sign, but in this case I don't flip the sign. And now we can just rearrange things. We've got therefore 1 is greater than 20E, which implies that E is less than 1 over 20. Okay, and that's it, we've done it. E is less than 1 over 20, and then in fact, don't forget, hidden inequality, we know E is always greater than 0, so include that as well, and our final answer will be E is greater than or equal to 0, but strictly less than 1 over 20. And that's it, that's the answer. Okay, and then part C. Let's clear up some more space. It's quite long, this question. Yeah, let's keep that as our main info. Let me just get rid of this. Just clear things up a bit. Right, part C. Given that the magnitude of the impulse of P on Q is that expression, find the value of E. So first we want to write that mathematically then, I suppose. The magnitude of the impulse of P and Q, P on Q. So in other words, the change in momentum of Q, right? It actually doesn't matter that P caused it. The point is Q changed its momentum due to the influence of P. So the change of momentum of Q is therefore, that's our object 2. Let's just call it 2. That's equal to its initial momentum, sorry, its final momentum minus its initial, which in our case, how much do we know there? Final was V2 and its mass was 4m, and its U2 was minus 2U. Okay, I'm just going to get rid of this bit because having m and 4m is a bit confusing. So that's equal to 4m V2 plus 8m little u. Now remember, that little u there is a scalar, but that V2 there is still a vector, just in case it matters. So this is basically in terms of stuff we know, but this V2, that's what we found here, isn't it? That one was V2. So we're going to have to put that in there. Okay, I've got to the point now where I just want to get rid of this bit. There's not enough space otherwise. So we're going to write 4m v2, where v2 is u over 7, 15e plus 1, and we're going to add 8mu. So now that's our expression. What's it in terms of at the moment? M and u, which is what we want in the final answer. We've still got this e though. But we're told this is equal to 80mu over 9, right? So presumably the m's and the u's are now all going to cancel nicely eventually. So let's bring the u out here actually. Get rid of that u there. Let's change it to 1 and change that 4m to 4mu. And then what else can we do to make this a bit nicer? I think since we're trying to hone in on the e, let's bring the 7th outside as well actually. Right. So now, perfect. Okay, we can get rid of the m's and the u's. Divide by m and u. Here it's gone, and here it's gone, and here it's gone. Perfect. So now all we're left with is numbers and e. So we're going to do 80 over 9 minus 8 times 7 over 4. Times 7 over 4, and that is all equal to 15e plus 1. What's that equal to? Okay, so time for you to try some questions yourselves. 4 questions, 2 on this page, 2 on the next, 1 of which is a challenge. So definitely try and get to that. I think you've got time for it. Give these 2 a go first. Pause the video now. Okay, and then harder set, getting quite tricky, particularly with that challenge. See how you do with these 2. Pause the video now.